Assalamualaikum warahmatullahi wabarakatuh. So let's start our lecture today. So we have arrived in week 13, right? Week 13. It means that we only have two material left before the final exam. The first one is OFDMA. So last week we have already learned about OFDM, and now this week we are going to learn about FDMA, and next week we are going to learn about single carrier FDMA or SC FDMA. Yeah. But before we start our lecture today, I would like to remind you again that we are still going to have a final exam for this course. So the marking criteria for this course consists of the first one is the mid exam, and also several assignments that sometimes I give to you every week, some particular week, and also the third one is the final project that you have to submit at 8 January 2020, and also the final exam. So that's the four grade marking criteria that you have to pass in order for you to get good marks, to get a full marks in this course. Okay, about this multiple access technique or FDMA, which means that it's orthogonal frequency division multiple access. So last week we have already learned about FDM, right? So if we're talking about FDM previously, it means that we are eliminating the guard band that is applied in the FDMA, right? So FDMA is the combination between FDMA and TDMA. However, besides combining both these two, we are eliminating each of its weakness. So if we divide it into a domain like this, if we divide it, OFDM, OFDM is divided into a two domain like this, while the horizontal one is the domain of time, and the vertical one is the domain of frequency. If we are looking at this, then we divided it into particular frequency, what we call as a subcarrier. This one is one subcarrier, right? And at the same time, we divided the time into multiple period. This one is the one period. If we are looking at this grid, then it looks like what we call as a resource element. One block like this represent what we call as resource element. And the multiple of resource element is what we call as resource block. We call as resource block, like that. Now, okay, so we got resource element and resource block. On the other hand, while in FDMA we implement what we call as guard band to eliminate intersymbol interference. So this is the frequency, the first frequency carrier, and we separated each of these frequency carrier by using what we call as a guard band. This is the second frequency carrier. Now, this is the guard band. Now, on the other hand, in OFDMA, we use a technique what we call as guard interval. And frequency spacing. So, if we look at the frequency domain in OFDM and OFDMA, we could eliminate this guard band by overlapping each of these frequency response. However, if we are looking at each of the peak of its frequency center, the next subcarrier has a zero power at that frequency range. At that frequency. If we are looking at this, the peak of this frequency center, if we call it the subcarrier over here is F0, and this one is F1, and this one is F2. Now, if we are looking at this, then F0 could be achieved at maximum value while the neighboring frequency response has reached the zero value at that frequency center. This is the zero value, which means that we could still eliminate the intersymbol interference. This process is what we call as orthogonal. So this is the process of the orthogonality. Okay, I have to close. Okay, this is the process of orthogonality. Nah, okay ya. Nah, in OFDMA, the technique used for radio transmission and reception in LTE. It's based on OFDM. OFDM. The carriers out the same functions as any other multiple access technique by allowing the base station to communicate with several different mobiles at the same time. So the technique is also the same. It allows the base station to communicate with multiple users, which means it increase capacity. On the other hand, it also allows a powerful way to minimize the problems of fading and interference symbol. Nah, this we have already learned about this. This is enabled by the concept of the orthogonality, right? By using the orthogonality of each frequency center of its subcarrier, we could minimize the fading and intersymbol interference. This one. Now, OFDMA is used by several other radio communication symbol system, such as IEEE 802.11. This is the Wi-Fi, right? Or wireless LAN. And also it's used by WiMAX, IEEE 802.16, digital television and radio broadcasting. Now, OFDM block diagram, if we could see, we have already learned about the OFDM block diagram like this. The additional block that is provided by the OFDM is comes from this part, right? So because we are utilizing multiple frequency subcarrier, so there is multiple modulation over here. This is for subcarrier 1, this one is for subcarrier 2, this one is subcarrier 3, and so on and so on and so on. Now, if we're looking at this, all of this modulation is separated into a serial to parallel, and then goes to the resource element mapping. It maps the resource, it maps a particular users into multiple resource element. Now, the process itself is also added into inverse fast Fourier transform or EFFT. And then it is combined again into a parallel to serial. And then it's transmitted over a channel, random channel. And the process in the receiver is the inverse of the previous process in the transmitter. The first one is this, it goes to the serial to parallel and then goes to the forward FFT, which is the inverse of inverse FFT. And then it goes to the resource element selection. It chooses the resource element according to particular user, and then goes to the parallel and serial, and then goes to the process of the demodulation. Now, all of this process only happen in the downlink. Why it's not happening in the uplink? Well, we are going to discuss about this next week. Nah, so this process only happen in the downlink, which is the communication between base station to the end user. Now we goes to the OFDMA. So in OFDM, there is a process to allocate each of the user into a resource element, right? Nah, in OFDMA, we allocate that into a multiple user according to the user. For example, in OFDMA, the base station shares its resource by transmitting to the mobile at different times and frequency, so as to meet the requirement of the individual application. So the base station maps the user or the mobile station into different times and different frequency. It allocates into several resource blocks. How big is the resource block? It depends. The resource block depends on the services. So if we are talking about voice over IP, for example, or if we are talking about browsing or streaming, it requires different bandwidth and different time. So the how large the resource block allocated into the user depends on the services itself given to the user. For example, if we are talking about voice over IP, the voice over IP is a communication of voice communication, right? It requires a dedicated channel. However, it doesn't need a large data rates. So, if we are talking about frequency domain over here, the vertical one is the frequency domain, right? It divided into several subcarrier, which each of its subcarrier wide is 15 kilohertz. Now, so uh, for voice over IP, we don't need a large data rates or low data rates. And because of that, the number of subcarrier allocated into the voice over IP is not that large. For example, the mobile one over here or the UE one, we don't need to allocate a large data rate. Thus, the frequency allocated itself is we don't need a very large subcarrier. We need only two subcarrier over here for voice over IP. However, for a voice over communication, we need a dedicated time, right? It means that the communication will always happen. People will always talking interchangeably. I mean that one people will talk and the other will listen. While the other is talk, the other one, that people will listen. So the communication need a dedicated time according to the length of the communication itself. So in the time domain, we could see over here, we block this resource block over here with a very small frequency subcarrier. However, we allocated all of this time period all over for one resource block for voice over IP. On the other hand, if we are talking about packet data, for example, browsing, in browsing, sometimes you do a browsing. What you do in browsing is you type Googling something, you enter, and then there is a transfer data, you read, and bit, when you are reading the content of the browsing itself, there is no transfer data happen, right? I mean that what you do is reading the content. So there is no interchanging data between the mobile station and the user. That's why we introduce what we call as a data burst. Data burst only happen, a large data speed happen in a very small time interval. So it only happen when we request the data to the server. There is a exchange of the data between mobile station to the user. That is what we call a burst of data. Burst of data only happen in a short period of time. Now, because it only requires a short period of time, on the time domain over here, we only allocate the time in according to how long the data burst happen. So in UA2, if we are looking at UA2 or mobile 2, this one is a UA2. When we are going to do a non-real-time packet data, the resource block allocated on the time domain is not fully served to that user. It's only according to how long the data, what do I call it? Transaction, maybe transaction or exchange. So the burst data only happen in the short period of time, right? That is the length of the allocation in the times period symbol that we are going to serve to the user. Wow. And the question is why it is needed large subcarrier compared to the voice over IP. Why does it need a large subcarrier? Now, because in data transfer, we require a higher data rate rather than the voice over IP. Because we need to transfer a large number of data in a very short period of time, as what we call as data burst over here. Data burst is we are transmitting a large data into a small period of time, right? A short period of time. That's what we call as data burst. Now, because data burst happen in a short period of time, we require a large data rate. As we have already learned about Shannon capacity theory, Shannon said that data rates equals to bandwidth times 1 plus SNR, right? It means that in order to get a large data rates, we require a large bandwidth. That's why this small subcarrier represent a bandwidth, right? 15 subcarrier, 15 kilohertz subcarrier, one resource element is equal to 15 kilohertz subcarrier. Obviously, if we are looking at this equation, this is the bandwidth is 15 kilohertz. Then, theoretically, we are going to say two resource block will have two times data rates of one resource element, right? It's obvious, right? Because we are using the Shannon equation. With the same value of SNR, we could see that by using twice the bandwidth, we could achieve twice the data rates. That's why in mobile 2, where the communication happen in non-real-time packet data, while there is a need of a burst of data in a very short period of time, we are going to need a large frequency, but with a short period of time. It's totally different with the voice over IP. Voice over IP is a very constant communication. However, it needs a long period of time. That's why we could see the red one over here. It requires a full time in this period domain, while in the frequency domain, it only requires a smaller one. Now, if we are looking at the other example, for example, the base station can also respond to frequency-dependent fading by allocating subcarrier on which the mobile is receiving strong signal. So in UE1 or mobile user 1, user equipment 1, we allocate the full time domain with the same subcarrier. This is the same subcarrier, we full it for a full long of time, right? We allocate this full time for one resource block for one UE1 for voice over IP communication. However, we could also divide this resource block into a separated block according to the response of its frequency dependent fading. So for example, in mobile 3 or UE3, mobile 3 is UE3, is using voice over IP communication same as UE1. However, it is affected by the frequency dependent fading. The fading happen in here, for example. There is a fading. This frequency is used by the UE4, for example. So if it's used by UE3, there is happen a fading, right? There will be fading happen to that resource block. Nah, in response to this, the base station allocates subcarrier on which the mobile is receiving a strong signal and changes, this is the key, it changes this allocation as the fading pattern change. Now, if we are looking at this, rather than blocking all of this period in one particular subcarrier, like the UA1, we could divide UE3 into different subcarrier. So in this period, they are using this subcarrier over here. And the second period over here, because there is a UE for utilizing this resource block, we put the UE3 in other subcarrier over here. In the third period, we allocate into different subcarrier over here. And so on until the communication ends for mobile 3. Now, in similar way, we could also separate separate the mobile phone using two separate blocks of subcarrier, which are separated by a fade. Now, if we are looking like this, because UE3 is utilizing this channel over here, sorry, not this subcarrier over here, this resource element over here, then when user E4, UE4 want to use this resource block, when he need a resource block this large from this part into this part, then they could divide the UE4 into two separated resource blocks. Now, so the UE4 is separated into two resource blocks, the same with the UE3. So this is the capability of what the OFDMA. It's like that. So we could see that like that. So we could see that in OFDMA it could be very flexible. Rather than blocking the resource full on that particular subcarrier, we could also separate each of these user according to the unused resource block at that time that is not affected by the fading. Now, by allocating subcarrier in the response of to change in the fading pattern, an OFDMA transmitter can greatly reduce the impact of time and frequency dependent fading. So it could avoid the frequency dependent fading by flexibly allocating the subcarrier according to the user. However, the process require feedback from the mobile. I forgot to tell you that the most important things in LTE or FDMA is one subcarrier is using 15 kilohertz. When one period symbol is using 66.7 microsecond. That's the important technical aspect you need to learn. Now, now we go to the fractional frequency reuse. In fractional frequency reuse, we have already learned from starting from 2G, 3G, 4G, and the next generation 5G. All of this generation consists of the same things. What is it? The same things, the same concept happen to this communication, especially the wireless communication is one base station can always send information to a large number of users. So, we only need one base station over here. It could communicate into a multiple user at the same time. UE1, UE2, UE1, UE2, UE4. Yeah, it's not limited to 4, but it could be multiple, a large number of mobile, a large number of user. Now, every mobile has to receive a signal from one base station in the presence of interference from the other. So, the interference not happen from this cell, right? Because obviously each of the user is utilizing different subcarriers or different carrier. However, if we are talking about other base station or other cell neighboring from this one, if this one is using the same frequency, F1 and F1, then there will be an interference between this part and this part. Obvious, right? For example, if this two base station is using the same frequency, then there will be an interference happen, especially to the user that is standing at the border of each cell. If we are looking at this user over here, for example, this one is UE5, then the large, how big the signal that gets from the base station over here to the base station over here is nearly the same. I mean that this base station could be an interference to this one or the other way around, depending on where the user is assigned to which base station. So if the user over this one is communicating using this base station over here, then this one will be an interference to this communication. On the other hand, if this cell is communicating to this user, uh, this base station over here will become an interference to this communication, to that communication. Nah, because of that, we need to minimize the interference so that mobile can receive information successfully. In the previous generation, the GSM technology, we are using the TDMA, right? Nearby cells transmit using different carrier frequencies. Typically, each cell might use a quarter of total bandwidth with a reuse factor of 25%. Obviously, because it's a quarter of total bandwidth, so each cell is allocating 25%. This one is 25%. This is 25%. This is 25%. That's why we eliminate the interference because between these four cells has different frequency. Now, this technique reduces the interference between nearby cell, but it means that the frequency band is used inefficiently. Sorry. Now, in the third generation or UMTS, each cell has the same carrier frequency with a reuse factor of 100%. However, the trade-off of this reuse factor of 100% is the increasing interference in the system. However, the bandwidth utilization is more efficient, right? Because, obviously, because we utilizing all of this bandwidth, it means that we could achieve a large number of users within one cell. Now, on the LTE, we use the same concept in UMTS. Every base station can transmit in the same frequency band. However, it allocates the subcarrier within that band in a flexible way using fractional frequency reuse. Now, if we are looking at this, for example, the total bandwidth over here is 100%. Total bandwidth. This is the 100% total bandwidth. So in LTE, it divided into inner circle and outer circle. This red one over here is inner circle, and the darker one outside it is the outer circle. In LTE, we are using 100% frequency in inner circle in order to minimize the interference from the other cell neighboring to it. So, if we are looking at this inner circle over here and inner circle over here and inner circle over here, it is separated by the outer circle, right? Now, 50% of this total bandwidth goes to the inner circle. How about the other 50%? The other 50% is divided into 3. The other 50% is divided into 3 frequency subcarrier. And it is allocated into different cell. So, if we are looking at this one is F3, this one is F1, this one is F2. Nah, if we are looking F1, F2, F3, there is no interference between this neighboring cell, right? F1 will neighboring with F3 and F2, but it will not neighboring to the other with to the other cell that is utilizing F1. So the distance between F1 over here to this one will avoid interference between same frequency system. However, on the other hand, we could still achieve 100% frequency reuse by utilizing it inside this inner circle over here. This is the concept of the LTE system. Every base station is controlling one cell, and every cell is sharing the same frequency band. Within that band, each cell transmits to nearby mobiles using the same set of subcarrier denoted F0. F0, this one is the inner circle we have discussed earlier. The mobiles are close to their respective base station, so the receive signal are strong enough to overwhelm any interference. Distant mobiles receive much weaker signal, which are easily damaged by interference. Nah, so to avoid this neighboring cell can transmit to those mobile using different set of subcarrier. So if the user is close to the base station or inside the inner circle, it doesn't matter because it has no interference at all, right? The strength signal is strong. The strength signal is strong. What does it mean? Okay. The signal is still strong because it's near the base station. Okay. Thus, the thing SNR, the interference from the neighboring cell will be very small because the distance itself is obviously far, right? That's why we could still achieve 100 frequency reuse by using the inner circle over here. There is a small interference because it is still near to the cell. However, on the further distance to the cell itself, the outer circle, in order to avoid the interference, we could transmit to the mobile station using different set of subcarrier. That's it. The F1, F2, and F3. Half the frequency band is reserved for nearby mobiles, while the remainder of 50%, all of the other half, is divided into 3 frequency F1, F2, and F3 for use by distant mobile. Resulting reuse factor is 67%. This is what we have discussed previously. 50% goes to the F1, 50% goes to divided into 3 frequency outer circle. This is the concept of the LTE. Nah, okay, this is the same. This one is 50, 0.5. This one is 0.5, 50, 50. Nah, okay ya. And then the channel estimation. In LTE, especially in FDMA, so wait, okay, in FDMA, so besides the main process of in FDMA over here, we add what we call as a cyclic prefix insertion. This is the cyclic prefix process introduced in OFDM and OFDMA, right? What is the cyclic prefix? Cyclic prefix is the guard interval or guard period to separate between each of its subcarrier in order to avoid interference. Nah, the other extra process for EFDMA is by utilizing the channel estimation and equalization. The transmitter insert a cyclic prefix into the data stream, which is then removed in the receiver. So the process is also the same. It adds cyclic prefix or the guard interval, yeah, the guard interval over here before the symbol is transmitted. This is the guard period or guard interval, the same. Now, then it remove the guard interval in the cyclic prefix removal in the receiver side. Now, the channel estimation function is each subcarrier can reach the receiver with a completely arbitrary amplitude and phase. Now, we could estimate the channel by injecting a reference symbol into the transmitted data stream. Now, in the receiver itself, it measures the incoming reference symbols and compare it with the one transmitted. It could compare the reference symbol into the transmitted one. Because of that, it could use the result to remove the amplitude change and phase shift from the incoming signal. Now, on the other hand, the amplitude change and phase shift are function of frequency as well as time, and it affect the different subcarrier in different way. To ensure that the receiver can measure all the information it requires, the LTE reference symbol are scattered across the time and frequency domain. So if we are looking at this resource block, this one is T, this one is F. So the reference symbol is scattered across the time and frequency domain. Nah, it is allocated around this part. Nah, however, the reference symbol only take up about 10% of the transmitted data stream, so do not cause a significant overhead. Obviously, in order to avoid overhead, then the reference symbol should not take up larger than 10% of the transmitted data signal. So this one is the reference symbol. Okay. Now, the next one is the cyclic prefix insertion. We could use the cyclic prefix in order to get rid of the inter-symbol interference. The method used in cyclic prefix is inserting guard period or GP before each symbol in which nothing is transferred. This one is the GP, this one is the symbol. Now, the GP has a function like a guard band. We could avoid inter-symbol interference by introducing this guard period. The guard period has a function to shield the symbol from the delay spread. Then the receiver can be confident of reading information from just one symbol at a time without any overlapping with the symbol that precedes or follow. So if we are looking at the symbol over here, for example, this one is the guard period and this one is the symbol. If there is a delay happen, so this part is the delay, right? Now, we could still achieve a good result as long as the delay itself is smaller than the guard period. So we still have guard period to shield the symbol from the delay spread happen from the communication. The reason of the delay, obviously, it comes from the inter-symbol interference. One of this method is the multipath. Multipath cause the delay, right? Because each of the signal have different path. It means that it will arrive at the different time on the receiver. That's why delay happen. Besides of multipath, there is also a mobility of the user, which means that from the mobility itself, it will causing a Doppler spread or shifting in frequency. Now, however, we are going to talk about the delay first before we talk about the Doppler spread. Now, because of the multipath, it causes a delay spread, right? Now, the function of the guard period itself is to shielding the data from this delay. Thus, the delay itself will be contained within this guard period, as long as it's not larger than the guard period itself. Now, the symbol reach the receiver at different time on different ray, and some extra processing is required to tidy up the confusion. Okay. Now, in LTE system, LTE use a cyclic prefix insertion. However, rather than using a blank guard period, previously we have the definition of the guard period is using an extra guard period which nothing is transmitted, right? However, in LTE, it's not nothing is transmitted, but it copies data from the end of the symbol following so as to fill up the guard period. Rather than sending the guard period by a blank symbol, it is transmitting the and copying the data from the end of the symbol following it. On the receiver side, if the cyclic prefix is longer than the delay spread, then the receiver can still be confident of reading the information from just one symbol at a time. So as long as the cyclic prefix or the guard period is still larger than the delay spread. Nah, so we are looking like this. The GP over here has nothing transmitted. However, in LTE, in cyclic prefix LTE, it copies this part into the guard period. It copies this part into the guard period. That's the function of cyclic prefix in LTE. Now, the transmitted signal is a sine wave, which means that amplitude and phase change from one symbol to the next. As noted earlier, each symbol contains exact number of cycles of the sine wave. So the amplitude and phase at the start of each symbol equals the amplitude and phase at the end. Because of this, the transmitted signal changes smoothly as we move from its cyclic prefix to the symbol following. That's the function of copying the end of the following symbol into the cyclic prefix or the guard period. Nah, the receiver in multipath environment, the receiver pick up multiple copies of the transmitted signal with multiple arrive time. This is caused by the multipath, right? These add together at the receiver antenna, giving a sine wave with the same frequency but different amplitude and phase. It's the total of all of this multipath signal received at different time. The received signal still change smoothly at the transition from a cyclic prefix to the symbol that follows. There are a few glitches, but these are only at the start of the cyclic prefix and the end of the symbol, where the preceding and following symbols start to interfere. Nah, the receiver processes the received signal within a window whose length equal the symbol duration and discard the remainder. If the window is correctly placed, then the received signal is exactly what was transmitted without any glitches and subject only to an amplitude change and a phase shift. However, the receiver can compensate for this using the channel estimation. This is the function of the channel estimation and equalization from previous block. Admittedly, the system uses multiple subcarrier, not just one. The subcarrier do not interfere with each other and can be treated independently, so the existence of multiple subcarrier doesn't affect this argument at all. So it's obvious, right? Because we are using multiple subcarrier that is using different frequency, then it is not interfering at all. Nah, LTA use a cyclic prefix of about this one is 4.7 microsecond. This corresponds to a maximum path difference of about 1.4 km between the length of the longest and shortest ray, which is enough for all but the very largest and most cluttered cell. The cyclic prefix reduce the data rates is about 7%, but this is a small price to pay for the removal of intersymbol interference. Nah, where is this 7% comes from? What do you think? Cyclic prefix 4.7. How long is the period symbol over here in LTE? Is 66, right? We could see that here, one period symbol in OFDMA consists of 66, what is it? 0.7 microsecond. Oh, where? 66.7 microsecond. That's why the data rate is reduced by 7%. Because 4.7 from 66.7 is allocated for the cyclic prefix. Nah, 66.7 is the period symbol of one resource element. Nah, we reduce the data rates of about 7%, however, we remove the intersymbol interference. Nah, so let's summary this concept about multipath in LTE. there is a base station communicating to user over here. This one is the shortest path. Because the communication happen, because the signal is sent to anywhere, let's say there is a building over here. Nah, this is the longest path. Nah, in inter-symbol interference, in multipath, the signal is sent using multiple path, right, and received at different path at the user. Nah, the LTE accommodates this method by using the guard period or cyclic prefix. Now, the cyclic prefix itself could accommodate the distance between the longest path and the shortest path as far as 1.4 kilometer. So, longest path and shortest path has to be shorter than 1.54 kilometer. If it's larger than that, then the consequences is the delay. If larger than 1.4 kilometer, the delay will be larger than guard period. Then obviously it will causing a inter-symbol interference. However, 1.4 is enough for all but a very largest and most cluttered cell. It's fine. Now, use of the frequency domain. Let us now look in more detail at the way in which frequency mobile communication system use the frequency domain. In FDMA, a mobile has to measure the signal on one subcarrier in the presence of interference from all the other. To minimize the amount of interference, the subcarrier have to be separated by wide guard band. The need for this guard band implies that the system used the frequency domain in an inefficient way. Now, if we are using OFDMA, in the time domain, its subcarrier start life as a sine wave, but the modulation process makes its amplitude and phase change at interval of the symbol duration of 66.7 microsecond. What's the symbol over the phase? This broaden the signal in the frequency domain to a bandwidth of about T-1. In the frequency domain, the amplitude of each subcarrier oscillates either side of zero and crosses through zero at regular interval of T-1. Nah, it will become like this. If we are looking like this, then we could see that the signal is broadened into a bandwidth of about T-1. If we are looking at this, there is a spacing between the frequency center of each subcarrier over here. This one is subcarrier 1 and this one is subcarrier 2. The distance between this one is 15 kilohertz. Right. Then, if we are looking at this between two frequency center, between two frequency response, then we could see that the frequency response of the subcarrier 1 will have a maximum value when the next subcarrier or the previous subcarrier has reached the zero value at that frequency center. It reached zero value over here when SB2 has achieved max value. On this, at the same time over here, it reached the max value from this one where the neighboring frequency subcarrier has reached zero value on top of it. At that frequency, sorry, not on top of it. Okay. Now, the problem is what will happen when the user is mobile. As we know from previous lecture in Fedi, if the user is mobile or moving, for example, the ambulance is moving with a sound of sirena, neung, 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 something like that. It is the phenomenon of what we call as Doppler spread, right? Doppler spread. It means that the frequency is not at that frequency anymore. It is shifted into F plus minus FD. Depends on whether it is going far distance or nearing the object. The value will be, the frequency will be shifted larger or smaller than that frequency carrier. It means that because of the Doppler spread happen, the frequency will shifted into this place. Nah, effect of Doppler spread. So, LTE has accommodated the intersymbol interference caused by the time variance experience from the multipath. However, in Doppler spread, or the mobility of the user, we could see that if the frequency is shifted into, for example, FD value, shifted to the right or shifted to the left, it doesn't matter. We could see that when this peak value of this frequency response has not achieved when the neighboring frequency has reached zero value on it. It means that there will still happen an interference when the user is mobile. It's obvious, right? When the user is mobile, the zero value over here, because the frequency is shifted from this part to this part, then the neighboring subcarrier has not reached the zero value on that frequency. It has become a problem in LTE system because of the mobility of the user. Now, if we are looking at this, the subcarrier overlap in the frequency domain, but the peak response of one subcarrier coincides with zero of all the other. The peak response of one subcarrier coincides with zero of all the other. It means that it reaches zero when the peak frequency happen at that subcarrier. When subcarrier over here at the peak value, at this value there is zero on that, on the other subcarrier. The subcarrier has reached zero value and the frequency response. However, wait, what is it? Nah, because of that happen, because of that happen, this property means that OFDMI use the frequency domain in a very efficient way. And is one of the reason why the spectral efficiency of LTE is much greater than the previous mobile communication. It's obvious, right? Because in OFDMA, we separate the guard band, but we introduce this orthogonality value. Now, this method is what we call as orthogonal. The subcarrier with this property are said to be orthogonal, which means that we doesn't need a guard band. However, the frequency response has reached at that subcarrier has reached a peak value where the frequency response of the neighboring subcarrier has reached zero value and that frequency center. That concept is what we call orthogonal. Nah, choice of subcarrier spacing. How do we choose the subcarrier spacing as large as 15 kilohertz? Nah, the argument in the previous section work fine in if the mobile is stationary. If the user is not moving, then the previous scenario works well. On the other hand, if the mobile is moving, then any incoming rays are Doppler shifted to the higher or lower frequency. That we have already discussed earlier, in LTE system, it suffers from the mobility or Doppler shifted. This has become problem. Why? Because obviously we are having a mobile communication, right? It means that the user has to be mobile. If the user is not mobile, then it's not mobile communication at all. It has become a problem. That's why choosing the spacing frequency between this one and this one has to be important to accommodate Doppler split or mobility. Mobility. Nah, it has to be important. Why? Because when Doppler split happen, the frequency over here is shifted into this part, for example. Then it will not reach the value at that frequency where the neighboring subcarrier has already reached zero value. This one is already zero value, right? This one is null. This one is no response, right? Which means that that subcarrier has already reached the null value in this frequency response. However, in this value, it is not zero yet at this. Then it will causing the interference, right? Obviously, because there is still a response in that frequency from the neighboring cell. Sorry, not neighboring cell. From the neighboring subcarrier. Then it will obviously cause what we call as interference. Now, in a multipath environment, a mobile can be moving towards some rays which are shifted to higher frequency but away from the other whose frequency move lower. As a result, subcarriers are not simply shifted, instead they are blurred across a range of frequency. If a mobile tries to measure the peak response of one subcarrier, then it will now receive interference from all the other. We have therefore lost the orthogonality property from the previous section. It's not orthogonal anymore because when it shifted to this place, the frequency response from the next subcarrier has not reached zero value, right? Nah, it lost the value of the orthogonality itself. Now, thus deciding the frequency spacing is very important. Now, in LTE system, we design to operate with a maximum mobile speed of 350 km per hour. Kilometer per hour. In order to not make you confused, I will delete -1 kilometer per hour and a maximum carrier frequency of about 3.5 gigahertz. which give a maximum Doppler shift of about 1.1 kilohertz. So, we still allow, in LTE, we'll still allow a speed of 350 kilometer per hour. It is the speed of train, right? Obviously, with a speed of train of 350 kilometer per hour at the frequency of 3.5 gigahertz, the shifting frequency is still about 1.1 kilohertz. This is 7% of the subcarrier spacing, so it satisfies the constraint above. Now, we choose the delta F, or frequency spacing, as large as 15 kilohertz in order to accommodate this Doppler spread. So if we are using Doppler spread of 1.1 kilohertz divided by 15 kilohertz, then it is still utilizing 7% of the value of the subcarrier spacing. So it's fine as long as the user is only moving for 350 kilohertz. Now, okay. There is another constraint on the parameter used by the LTE. To minimize the impact of inter-symbol interference, we need to choose the symbol duration T as follows. As we noted earlier, LTE normally work with a maximum delay speed of 4.7 microsecond. This is 7% of the 66. Oh, I think we have already discussed about this earlier. So the multipath should be no larger than 1.4 kilometer, right? 1.4 kilometer is equal to 4.7 microsecond. Thus, it still accommodate 7% of the symbol duration. So it doesn't matter as long as the frequency shifting is not larger than 1.1 kilohertz or 350 kilometer per hour. If we convert it into speed, then by using in the time domain, it doesn't matter how much the multipath as long as the distance between the longest path and the shortest path should not be larger than 1.4 kilometer, or the delay should not be larger than 4.7 microsecond. Now, from this conclusion, we can draw the following conclusion. If the subcarrier spacing were much less than 15 kilohertz, then the system would be prone to interference between the subcarrier at high mobile speed. If it were much greater, then the system would be prone to inter-symbol interference in large cluttered cells. The chosen subcarrier spacing is the result of trade-off between these two extremes. So, to conclude our lecture today, OFDMA in LTE has already accommodated the two main problem of fading. The first one is the Doppler spread. It is accommodated by delta F, ya, delta F, which is 15 kilohertz. And the second one is accommodated, we avoid the time invariance or multipath or delay. It is accommodated by cyclic prefix. Oh, what's this? Cyclic prefix with a guard B, GP, or GB. As long as it's not larger than 4.7 microsecond. Okay, I think that's it for our lecture today. So after this, in order to improve your understanding, I will have some quiz in LMS. You could access the quiz itself on LMS. Starting from 1:30 at 2:30, starting from our lecture today at 2:30, you could access the quiz on LMS, and the deadline will do in 20 of December. Yeah, 20 of December is the due of this quiz, and you could do this quiz for 1 week. Yeah, so we have still 1 week for you to do this quiz. So if you don't have any question, then we are going. I think it's the end of our lecture today. So we are going to discuss this lecture next week together with the SGFDMA. If you have any question related to this lecture this week, okay. That's it for today. Thank you. Assalamualaikum warahmatullahi wabarakatuh.